Mm, Testing? Good, I can hear it from his phone. Okay, sorry for the delay, ladies and gentlemen, but today it is afternoon, is good afternoon. It is my great honor to introduce one of the brilliant minds in polymer chemistry in the field of flame retardants, especially my good friend, my great colleague, Dr. Gaan. And let me introduce a bit about Dr. Gaan himself. So he received his PhD in chemistry from UC Davis in 2007, and he has been working at EMPA since 2007 and is currently head of additives and chemistry group in the Laboratory of Advanced Fibers. His group specializes in developing additives for bulk polymers and coating, synthesis of polymer, and its recycling. His group has developed several phosphorus flame retardant in various commercialization stage, and he has over 140 scientific articles and 15 patents, a tremendous achievement. And his group was awarded the Innovation Prize in 2016 for successfully transferring technology to industry. The innovation was synthesizing a new halogen-free flame retardant, namely the EDA-DOPO, and its uses in polyurethane foams. So let's welcome Dr. Gan.
Good afternoon, everyone. It is actually a pleasure to be here. I have never been to Hong Kong before, and because I was traveling to China for a conference, I thought it would be a nice opportunity to come and visit PolyU. And especially, I know Anthony for almost 1.5 years or almost 2 years now. First met Anthony in a conference in Australia, where I was quite impressed with what they are doing, I would say. And the fact that the fire community in polymers is quite small, but when we meet each other, we are very, very, I would say, close. And the fact that he's a new member in the fire polymer community, it actually is a pleasure to come here and see what you guys are doing. Also, it gives me an opportunity to I would say see a new place. I would say, okay. So today I'm going to talk about something which is very recent in my team. We are working on covalent adaptable network, and also trying to address its fire performance. I will tell what is the motivation behind it, I would say. But what I like to I know that most of you guys are not chemists. Some of you probably work with materials, you are engineers, some of you are chemists, but majority of you are not chemists and mostly engineers. So my goal in this presentation is to give you an idea about what are thermoset polymers, how can we address their recyclability, but then we will also learn a little bit about how to address fire performance of these polymers, because it's quite important, I would say. And what are the mechanisms behind improving their fire performance? And can we combine both these technologies together and develop a material which is quite relevant for industry? So that's my goal, I would say. So if you see here in this video, there is a material. It's actually a covalent adaptable network. It's actually a vitrimer, to be very specific. And it's a thermoset. Normally, people would imagine a thermoset to be a set polymer. It should not change its shape when you apply heat. But this is a very special thermoset which can remember its shape and also recover itself when you apply heat to it. So you can see it is folding back and forth. You can do it many times, okay? But still, it's a thermoset polymer, I would say, okay? I'm going to talk a little bit about how you make these thermoset polymers, I would say, which have different applications. So, how do I move my slide? Okay. So where do I come from? Huh? So not a lot of people know EMPA. EMPA actually belongs to this bigger university consortium called ETH. And ETH, probably many people know, it is the 7th ranked university in the world. So, we belong to this domain, ETH, where EMPA is one of the independent research institute. We do have EPFL and ETH as academic institute, which is on top, you can see. And then you have EMPA, where I come from. We do have other institutes as well, which works in this domain. PSI, which does nuclear research. And then we have other 2 research institutes, which is more focused on doing aquatic research. And there is this Snow and Avalanche Research Institute as well. So in total, we have all these, I would say, organizations grouped into the domain, and ETH is the parent institute, I would say. Okay, so we are affiliated into this big organization. EMPA, unlike other institutes, we do not offer courses. We don't teach. We are an independent research institute where we are catering mostly to industry. So I mentioned EMPA. EMPA is in Switzerland at 3 different places. The main office is in Dubendorf, which is in Zurich. So when you fly in, you probably will most likely, when you go to Switzerland, you fly into Zurich. St. Gallen is east of Zurich, and we do have another small place called Thun, which is really south of Zurich, close to Bern. And all these 3 locations have different labs. Dubendorf has the most labs. I would say it has almost 25 labs. The remaining 2 locations, like St. Gallen, has around 5 labs, and Thun has 1 or 2 labs in total, I would say. So there are different labs at different locations, I would say, when you come. So I am actually coming from St. Gallen. You see this nice glass building. It's quite impressive, I would say. So what do we do here, I would say? If you look, this is the motto of EMPA. Huh? So the goal is to work with industrial partners. So you have an idea, you do research, you transfer it to the industry, and hopefully the industry makes money, and the money is fed back into the system, back and forth again. So unlike academic institute, we are more focused on industrial research, and the goal is to help industry, Swiss and European industry, make money with new ideas. So we are very close to industrial applications, I would say. But we start with a basic research in our mind and go all the way to applications. So moving forward, as I said, these are some numbers in the domain, I would say. Quite a lot of, I would say, professors are in this domain. In EMPA, we have at least, I would say, 1,000 employees. And these 1,000 employees, I would say 80% of them have PhDs or are doing PhDs, I would say, or the doctor studies, I would say. What do we address? You know, as you know, UN has this 17 goals, sustainability goals, and we do address to some of these goals directly via different projects. And it's very important for us to address these goals, I would say. A little bit about my team. As you can see, it's a very small team of around 14, 15 people. And we work on mostly polymer additives. So we make functional polymers, we process them, we make monomers. We also do a lot of synthesis. And more recently, we have been more interested in how to recycle polymers, not only thermoplastics, but also thermosets, I would say. So this is my team's activity. So if you see, a lot of this work has been on phosphorus chemistry, but we also synthesize polyolefins. We develop our own catalyst, and we are also interested in making polymers from these catalysts, I would say. We do have also publications on gel, so we do quite a lot of chemistry, but majority of these chemistry we develop are based on phosphorus, I would say. Obviously, my group is mostly known for flame retardant materials, so I'm going to go more into details, I would say. But today's topic is about covalent adaptable networks, okay? But before we go into this covalent adaptable network, I don't know, you are engineers, huh? Sometimes you have come across these polymers. There are different kinds of polymers. There are actually two main class of polymers based on their thermal behavior. So you have the thermoplast. When you heat them, they flow, they melt, they flow, and you can reprocess them again and again. So they are thermoplast. But then there are this other class of polymers, thermosets. When you heat them, because the fact that they are cross-linked, there are bonds between the chains. When you heat them, they cannot flow because they are bound to each other, okay? And then because of this nature, thermoplasts, as they don't have bonds, permanent bonds between the chains, they can be processed, reprocessed again and again. And you probably know polyesters are the most recycled polymer, I would say. You see the PET bottles are the most recycled polymer in Europe. I'm not sure about China. Maybe it's a different scenario. Maybe in Hong Kong, it's a different scenario. But polyester as such is a thermoplast which can be recycled again and again. But thermosets, if you look, are polymers which are cross-linked, and they offer a lot of advantage because they are thermally inert polymers and have very high performance. They are quite rigid and chemically inert, okay? And the problem is, at the end of their life, you cannot recycle them. So most of them are landfilled or they are incinerated. I was just discussing with Anthony, and it was mentioned that there's a lot of landfilling happening in Hong Kong. In Europe, there is a lot of incineration happening. And you can imagine you lose a lot of resources, you pollute the environment up and down, the soil as well. And that's nothing, but that's not in agreement with the 17 goals of UN. So if we need to do something, I would say, okay. These thermoset polymers, as I mentioned, there is a difference between the thermoset and the thermoplast, okay? The biggest difference is thermoset polymers are liquid during the application. They are like, thermoset polymers, actually, they are not cross-linked. Before they're cross-linked, they're liquid. So it's easy to impregnate, or apply them, I would say. And when you make composites, you need easy application. And when you have liquids, it's very easy to apply. So thermoset, before you apply them, are very, they are like fluid. They flow very easily. It's easy to apply at room temperature. Unlike thermoplast, you need to heat them to 250 degrees, 300 degrees to make them flow. And they're still quite viscous, I would say, okay? So the advantage of thermoset are they're easy liquids in the beginning, and then you can cross-link them, and you can see different applications. And a lot of these applications, for example, here, windmills, you produce a lot of windmills today because of energy requirement. It's a clean energy. But then what happens at the end of life? So the fact that they have to be discarded, landfill, it's not good. And they are all made from glass fiber reinforced thermoset composites, I would say, okay? And obviously you see a lot of phones, electronics, electrical equipments are also made from thermoset resins, where you combine different layers using the resin. And similarly, a lot of parts of aircraft and joining of metals requires, I would say, these thermoset resins. Okay, it's very easy to apply. Just remember that thermoplasts are not easy to apply. Okay, they have their own advantage, but thermoset do have the most advantage of thermoset is they are liquid in the beginning and you can apply them. Okay, and they are preferred for a lot of applications, which I just mentioned here, I would say. Okay, but of course, end of life, all these thermoset based materials, mostly they are composites and they are not easily separable. What do? You burn them, okay? And you try to recover energy, but also you landfill them, and which is actually a problem. So how do we solve this problem, I would say, okay? To solve this problem, I would say, many years back, people came up with, I would say almost 20 years back, a term called covalent adaptable networks were developed, okay? And there are two different kinds of covalent adaptable network. They're actually thermoset polymers under application or working condition. But when you heat this polymer beyond certain temperature or use different stimuli like pH or light, you can actually make changes in their structure. Okay, so there are two different kinds, as I mentioned, associative and dissociative. In an associative mechanism, when you apply a trigger to this thermoset polymer, you can see a bond is broken and a new bond is being, well, I'm talking about associative. So in associative, while a new bond is being broken, a old bond is I would say being formed or vice versa. So you break and make new bond at the same time simultaneously. Whereas in dissociative mechanism, you break first one bond and then you create a new bond. So you can imagine when you heat a associative covalent adaptable network will retain its material property at that temperature, higher temperature. Whereas a dissociative one, because you already break a bond while a new bond is being formed, you lose mechanical integrity of this material quite a lot. Okay, so you have to remember there are two kinds of covalent adaptable network, associative and dissociative, I would say. And this is the one, I would say people use different chemistry to, I would say, make these bonds. So I'm not going to bore you with all the details of chemistry. You can look at, there are a lot of different kinds of chemistry you can use if you're an organic chemist. For at least you know one of them, which is these, on the top right, you see this ester bond. So it is the most common, I would say, bond which people use for making different polymers, different resins. So an ester is made from an acid and alcohol. You combine them together, you do a dehydration reaction, you remove water, and this can go back and forth when there is another alcohol present on its side. Okay, and that's the most common bond people are aware of. Obviously, you also need a catalyst to do that. Okay, and so catalyst helps you in reducing I would say the temperature of this rearrangement reaction, I would say. But there are different kinds. We don't have to go into details. People may have heard about disulfide linkages, boronic esters. Then you have Diels-Alder reaction. So there are different kinds, but it's a kind of a toolbox you can use to make these dynamic bonds, I would say. If you're an organic chemist, you don't have to remember this, but just remember these few terms, I would say, okay? And as I mentioned, one of the important application of, I would say, flame retardant or epoxy on, or I would say thermoset material is to develop fire-safe materials. And in fire safety, one has to understand the materials. What do we do is to develop a material which is slow in burning, okay? Or at least it buys you some time, okay? Here in this case, you can see when you have a big fire, I would say on the left, if there is no flame retardant inside, it starts to, burn very quickly. So the time you have to escape the room is quite short. What you do is, when you add a flame retardant or you have a flame retardant material, you prolong the the initial phase where you have time to escape. So a flame retardant material is not a fireproof material. Okay, you just for people to understand, you just delay the burning process, slow down so that you have time to escape. Of course, everything will burn down. Okay, so just that you remember. So what we are trying to do is make things slow in burning, I would say. So you see there are different examples you have seen over the years where you see a lot of people died. Okay, most of the time in case of fire, people don't die because of fire, but because of the smoke being produced. Okay, so that is the problem, I would say. And this, if you can stop the fire in the beginning, or you can slow the fire in the beginning for it to make bigger fires, you actually can gain time, and people can escape. But the smoke is always the one which kills a lot of fire. So one has to understand that. So anything which makes less smoke is also good. Some flame retardants are good in suppressing the smoke, I would say. So that's also quite important, I would say. If you look at the different kinds of flame retardants, organic and inorganic, the world is dominated by inorganic flame retardants, okay? And they are cheap. You can see the oxides are quite cheap and quite, I would say, effective as well. But you need a lot of these additives. For example, in cable, you need up to 50% of aluminum hydroxide or magnesium hydroxide to make the whole system flame retardant. But then you have the organic flame retardants. These are like the halogenated ones, which probably are problematic. It has to be replaced at one point. But then you also have organophosphorus ones, or phosphorus-based flame retardants, which are considered to be a good compromise between toxicity, performance, and price. Okay, it doesn't mean that they are all good, I would say. You just have to look and see which of them meets your requirement, I would say. Okay, want to give a real, I would say, idea about how does flame retardant work, because it's very important later in my presentation. So when a material burns and there is no flame retardant, it releases volatiles. I think it's the material which doesn't burn. It's the volatiles which are produced due to thermal decomposition. They get oxidized, and the oxidation process then feeds the heat back to the substrate, and this loop goes on forever if you interfere with this process by adding a flame retardant. So the flame retardant could be added on the surface of the material, or it can be in the bulk. And in case it works by intumescent or coating mechanism, you form a kind of a thick barrier on the surface, and this prevents the volatiles from being released, and that way you can prevent the burning. Or the volatiles which are being produced also produces quenching radicals. These radicals interfere with the oxidation of the volatiles and or the flammable volatiles, and you prevent the burning process. So basically, halogenated flame retardants, phosphorus flame retardants also release radicals which can recombine hydrogen and hydroxyl radical, which are actually the main combustible additives or combustible, I would say, component, which can be recombined to form water and prevent the burning process. So this is the basic mechanism, I would say. Phosphorus flame retardants can work in condensed phase and in gas phase. In condensed phase, they form this aromatic char, which forms a barrier on the surface. And in the gas phase, they form phosphorus oxide radical, which can then recombine hydrogen hydroxyl radicals. You can say it's a catalytic process, I would say. Okay, so this is something you have to know, I would say. But one has to understand the way the phosphorus flame retardants work depends mostly on the polymer which you're using. So if you have a hydroxyl containing polymer, the phosphorus normally does the dehydration reaction and you form char. And if you have a oxygen-free polymer like polyolefins, the flame retardant action of phosphorus is more in the gas phase, I would say. Okay. So coming back, can we combine recyclability and phosphorus, or flame retardancy in one polymer for different applications. Yes, there are a lot of work being already done by different groups. So we are not the first ones who have addressed these things at the same time. You can see there are different ways people have tried to address this polymer. They have addressed this polymer by having FR in the polymer as a side chain, or if they have provided FR in the polymer as a backbone. Okay, so there are different strategies already available. People have used phosphorus-based flame retardant. They have used sulfur-based flame retardant. The problem with all these flame retardant strategies or recycling strategies is a very complicated synthesis process has been used. And in some cases, the fire performance has not been good. But in many cases, it has also been very difficult to achieve good mechanical performance. Okay, so there are a lot of shortcomings of these inherently flame retardant recyclable thermosets, I would say. Okay. So what we developed in the past, we have come up with a new kind of chemistry called phosphonate or phosphine oxide chemistry, which offers inherent fire protection. It's upscalable in industry. You can see the material is actually recyclable back and forth. We have patented it and we also published it. And I'm going to go through some of these application or chemistry. So the first chemistry is in the beginning, I showed you people have come up with all kinds of covalent adaptable network chemistry. So we were the first one to develop this phosphonate chemistry. A phosphonate chemistry is phosphorus based. You can see phosphorus is linked to 2 labile PO bond and 1 permanent carbon bond. So what we do is we fix this chemistry inside the thermoset resin by playing some trick. I will show you how we do it. And the fact that there are 2 labile bonds and there are alcohols sitting around it, you actually can do reversible reaction. So these are phosphoester reaction. You can see on the right, you see an alcohol is attacking the bond, existing phosphoester bond, and you make new bond. While the new bond is being made, you soften the material and you can reprocess it by thermal action, I would say, okay? Don't want to go into details. How do we make this? So to do this, you need a special monomer. In our case, we have this cyclic phosphoester monomer on the top, I would say. You can see on the left. And it's actually a reactive monomer which reacts with the epoxy resin. And then it is hardened with an amine. So you need all these 3 components to make a network which is dynamic in nature. And the dynamic bond is this green parts where phosphorus is connected to a carbon and it's connected to 2 oxygen at the same time, okay? And the material is transparent in nature. And you can see by having phosphorus, different amount of phosphorus in the resin, you can see you can influence the thermal property of the material. You tend to have very high char when you have higher phosphorus. You can see this violet curve, I would say. This has the highest char because it also has the highest phosphorus, I would say, in the structure. However, when you have higher phosphorus, you also have lower thermal transition temperature, which is glass transition temperature, which is TG of the material. So you need to be aware of it. And what is very important in case of vitrimeric or in case of covalent adaptable network is the transition temperature. So the transition temperature is something which we try to measure, okay? And we measure it, it's a temperature at which the viscosity of the polymer or the material is below 10 to the power 12 Pascal second, okay? And that is the temperature where you are able to reprocess the polymer. So we need to calculate that, okay? And what we also calculate is activation energy. How much energy is needed to make this, recreate this bond. And it is in a very good region of 75 kilojoule per mole. And what is also important is you need to know there is a certain amount of phosphorus you need to get this recyclability, I would say. Okay. So take home message. Higher the phosphorus, easy to recycle, but also lower is the glass transition temperature. And higher is the char content of the material, I would say. So you can see at 6% phosphorus, you are able to make a material which can be recombined back and forth, broken many times using heat treatment and heal the material. Also, the material itself is quite transparent, you can see, and you can powder it and press it back again as well. So you can actually recover the whole polymer back and forth. And this is because there is this covalent adaptable network from the phosphorus chemistry, which we have incorporated into the resin, I would say. Of course, I showed you how the recyclability works, but does it work as a flame retardant? Because that's also our goal. You can see to get recyclability, you don't need as much, get fire protection, you don't need as much phosphorus. You need less amount of phosphorus. Okay, that is something which you have to keep an eye. On the left, it is a resin, epoxy resin, which is actually burning, dripping. On the right is the dynamic network, which has 2.5% phosphorus, and it doesn't burn, I would say. Further, when you do a cone calorimeter test, you can see the amount of heat produced is quite low. The new polymer or the network also produces a lot of char and inhibits the burning process. Okay, so what is very interesting is, unlike many flame retardant system, this system produces less smoke as well. So when you work with flame retardant materials, normally you also increase the smoke. That's a normal side effect of a flame retardant. But in our case, the fact that we produce a lot of char, we reduce the smoke, I would say. And there is a reason why. You have a lot of condensed phase activity where phosphorus acts by making dehydration reaction. It produces a lot of aromatic char on the surface, I would say. And that's what you see. So we looked into different applications. One of the application was to apply this thin coating on wood surface, where you can see on the left, there is a IR camera at the back. You provide a flame on the front, which actually you can see the experiment. We apply like 5 minutes of flame, and you can see the maximum temperature, which is can be recorded at the back of the material, which has got this coating, is up. It's not more than 100 degrees, I would say. Whereas for a untreated wood, which has no coating, you can see it just burns through. So it's a very nice example of how to use this kind of resin. And the fact that it is transparent for many wood application, you want to see the structure of the wood. And that is where it is very interesting, I would say. You can have transparent coating and very thin coatings, I would say, which prevent of the polymer. I'm going to also highlight the fact that you can use different chemistry. So with the same idea, you can flame retardant different chemistry. So if you are working with epoxy resin, you can have epoxies, different kinds of epoxy. You can have different kinds of hardeners. Does our system work with different chemistry? Here I can say that yes, our system works with different chemistry. You can see the dicey is another kind of hardener. You can also use that hardener, and you end up getting a recyclable material and also a material which has got a UL94V0. It's a versatile technology. So you can use any kind of epoxy resin, a different kind of hardeners, combine them, but you still need the monomer, which I showed you, the cyclic monomer, and you will be able to get flame retardant material. Of course, the material is scratch resistant. You can see we made a big scratch and then tried to heal it. Obviously, it is not able to completely heal the structure because you remove the material while you did the deep scratch. But you still see that it is able to recover quite a lot. And also a repeated heat, you can break and you can recover the structure back and forth again and again, I would say, this epoxy. I'm not going to go into details of there are challenges to this system, just to know that not everything is so easy in when you develop new materials, I would say. So for example, here, I just want to give you that this monomer here, this one here, which is very important for our system, is quite difficult to make. It's not so easy, okay, for industrial upscaling process. It is not so easy. I just want to highlight that. But then we resolve this problem by developing smaller phosphites. I'm not going to go into the chemistry, but the end result is we are able to resolve this problem with different idea. That the monomer is difficult to make, but then you start with something else as a starting material, I would say. But you get the same results, I would say. We could also use, not only for coating application, but we can also use the resin to infuse fibers and make composites. Okay, so you can see here we have jute flax fibers composite, and when you make composite, you remember you always have waste because you have to cut, and this waste is trashed in industry. But what you can do is you can grind them and form a new different kind of part because our resin is recyclable. Okay, so obviously you will be wondering, you have good fire performance, but the mechanical properties go down because you go from a continuous fiber system to a small fiber system. That's why the final application has to be in mind, I would say. When you grind, you break the fibers, you lose the mechanical integrity. So that's a drawback of the system, but you still can reuse the whole material, I would say. Obviously, as a downgraded product, I would say. We can also resolve the problem by not only making small phosphite, but make polymeric phosphites. And this polymeric phosphite can then react and form resins, I would say. I don't want to go into details, I would say. And you still more phosphorus, more char, which is very interesting. Obviously, the glass transition goes down, the more phosphorus you add, just that you know about the side effect of having these phosphorus species, I would say. You get a UL94V0, very easy. You need to, the rating, in this case, when you use polymeric phosphorus compounds, you need 3% phosphorus to get a V0, but for recyclability, you need around 4 to 5% phosphorus. Here you can see we do have challenges as well. When you have higher phosphorus content, it's easy to recycle them, but then after 10 recycling, you see this blooming effect, I would say. That's something we need to consider. Whereas for 6% phosphorus, you see 10 times recycling is possible, but we also see side effects, I would say. The material integrity goes down. So this is something we are trying to understand why this is happening. Obviously, you can recycle them, but we want to have a recycled product with similar material integrity. So we are still understanding what's going on there. However, when you have a little bit less of a phosphorus, like 4%, you can recycle it 10 times. Yellowing happens because you're heating to temperatures which are quite high, 240 degrees. Higher the phosphorus, lower is the reprocessing temperature, and vice versa. So 4% phosphorus requires higher temperature of reprocessing, which leads to yellowing because these resins all contain nitrogen in the structure. Okay, so you need to know your system very well. It's very important, I would say. Going forward, what else can we do with this? So these resins can then, I showed you, it can be used to make, I would say, fiber reinforced composite. In this case, this is glass fiber reinforced composite. Normally, what you do is you impregnate each layer of a glass or carbon fiber with this resin, and then you stack them on top of each other and you press them into a composite. That's how you make composites, okay? However, end of life, for example, carbon fabrics, they are pretty expensive. So these carbon fabrics, it would be nice to recover them. And the price of a carbon fabric could go up to $200 per kilo. So imagine you want to recover this precious raw material. And the way we do it is by removing the polymer, which is in between this fabric, by alcoholysis process. So in our system, we put the composite in an alcohol, heat it up, and it opens the structure, okay? And when it opens the structure, you can separate the fibers and recover the fibers. So, and this is called chemical recycling. In the previous case, I showed you all the thermal recycling process, where you just heat back and forth, but then you downgrade the material. In chemical recycling, you need more energy, you need a little bit of more chemical, but you can, I would say, recover fully your fibers and also the polymer at one point, I would say. You can see in our case, you can just heat up and you can dissolve the polymer quite easily in alcohol and recover it, I would say. What else can you do? So you know that epoxy resins are used, or thermoset resins are used for bonding of materials. Okay, for example, in automotive industry, you bond different parts and you want to recover these parts, I would say, at the end of life. So here I show you a demonstration where two glass slides are bonded with this resin. Okay, you can they are bonded. And then if you want to recover deassemble the part, you just have to heat it up to a temperature beyond the what do you call the V-trimmer processing temperature. It's a TV, I would say. And then you can separate the material. So it's a glue which is debondable. Okay, so you can go back and forth with different kinds of chemistry, I would say. What I showed you was a covalent adaptable network where phosphorus was part of the network, was built into the network. Here, you have another chemistry which is called carboxyester chemistry, where the phosphorus is not directly part of the network. The phosphorus is not the one which links the different polymer networks. Okay, so here this is a chemistry which is also amine-free. It uses an acid, a bio-based acid, to network the structure, and it's called carboxyester chemistry, where phosphorus is dangling to the side, I would say. Okay, so in this chemistry is also quite recyclable. You can see you can break it, repair it all as many times. You have very high mechanical performance even after a few times of recycling, I would say. And the glass transition temperature also is quite high, I would say, for this system. So it's another chemistry where phosphorus is not directly linked to the network. It is on the side, I would say. Okay, and obviously you can get very high fire performance on the right. You can see you can get high LOI. You can also get a V0, but you need 3% phosphorus to get this. And in this chemistry, the action is more in gas phase, where the phosphorus is being released in the gas phase, and it quenches the radical, I would say, very much. You don't form a lot of charge, so it's another kind of chemistry, but it's a carboxyester chemistry. More recently, we have developed a very complex chemistry called an amino ester covalent adaptable network. You can see I have marked two different bonds here. On the left, you can see there are two networks. One is these amino ester bond. These amino ester bonds are mostly working via dissociative mechanism, where one bond breaks and a new bond is formed. While at the same time, you have a carboxyester chemistry happening where new bonds are formed at the same time as old bonds are being broken, I would say. Okay, so you have two different chemistry in the same material, associative and dissociative. And this is, how do we do it? So we do it by, we take a amine, I would say, and we react it with an acrylate, and we do a Michael addition reaction. And this Michael addition reaction is reversible in nature. You can see here, this Asa-Michael addition reaction is reversible when you heat it up. Whereas you can see the other part does the associative mechanism. So this is a new chemistry we have developed, and based on this, this work is still not published yet. What we did was we took this chemistry and we added our own additive to this resin, I would say, and we get completely a different kind of thermoset resin, which works by a very complex chemistry where you have two different dynamic bond actions happening at the same time. You get a recyclable material. You can see you can recycle it 10 times and you don't lose any mechanical property. It looks exactly the same as virgin material. And in this case, interestingly, you need only 0.6% phosphorus to get a V0 rating. Because in the past, I showed you some examples where you need 2% or 3% phosphorus. Here you need very small amount of phosphorus. And of course, you can use this to make fiber reinforced composite. What we did was we can do full recycling of this material. So you make a composite material. How do you recover the fibers? So unlike alcohols, you do aminolysis here. So you add it in an amine. And what amine does is it opens up the bond, I would say, and you can recover the fibers. You dissolve the polymer away and you recover the fiber. But at this moment, we are not able to fully recycle the polymer yet, but we can recover the fiber very much. So this is unpublished, this work, but you can see that the aim is to be able to close the loop fully, I would say, with this kind of chemistry. So it's not alcoholysis, this is aminolysis, and this network is amino ester network. So you can go back and forth, I would say. So I'm towards the end of my presentation, I would say. One has to understand when you want to recycle, when you want to go from a linear economy to a circular economy, the bigger the loop, the more energy you require, okay? And that's something we have to pay attention to it. I would prefer personally to be in the smaller loop because you require less energy, you reuse the material as much as possible, and obviously at one point you can make the circle bigger and bigger, but you should know making the circle bigger means you need more energy, more resources are required, okay? And so one has to be aware of this, I would say, okay? So at the end, this is the last slide. I showed you an example of, or the principle of covalent adaptable network. These are thermoset polymers, which you can open and close by using different triggers. In our case, we are using thermal trigger to rearrange the polymer. You can also use heat and light. And we are focused on this phosphorus-based chemistry where, phosphorus-oxygen bonds are reversible. We also have used carboxy ester chemistry. More recently, we are working on amino ester chemistry where you make a nitrogen-carbon bond, which is reversible in nature. So I showed you different chemistries are available. Obviously, not all these chemistries offer all solutions, okay? So you need to understand what is your material characteristic you want. So you take the chemistry and try to adapt it to the material you want to, or material performance you need to achieve, I would say. Obviously, I cannot finish my presentation before thanking my colleagues here. You can see the phosphonate chemistry were developed by Venue, which actually is a scientist in my team. The polyphosphide chemistry is being developed by Arvind in my team. And more recently, Sed is working in my team and he's developing the amino ester chemistry. We did have a visiting scholar. He's back in China now, Zhenyu. He spent some time working on the carboxy ester chemistry. Okay, and obviously Sandro and Miliana are the core of the team. They do all the analytics, take care of all the difficult, I would say, problems like, for example, all the fire tests. It could be very time-consuming, laborious in nature. If you have run cone, You need to clean the instrument every time you burn epoxy resins. It clogs the filter, so it's quite difficult, and they really need to do hard work, and I really thank them. And Sandro actually is responsible for all the analytics in the lab, which could be thermal, chemical, NMR, all kinds of tools I have. He's the one who takes care of all this. Without these two guys, I'm not able to develop new materials, I would say. So obviously I cannot finish my presentation without thanking the good time I had yesterday, I would say. Enzo and me had a good outing. You can see we could take some nice pictures. And at the end of the day, we actually had dinner at an Indian restaurant. I already baptized him in Indian food. I would say he did. I hope he enjoyed the food, I would say. And yes, I cannot thank you guys for taking care of me while being in Hong Kong. I really appreciate. I also like to thank Anthony from the very day one. He has been very kind in organizing all the stuff. And obviously, I am really thankful to you guys for listening to me. I hope I could teach you a little bit. I would say, of course, I know this is very difficult. There's a lot of chemistry involved, but I'm more than happy to answer any question. But by the way, this nice building at EMPA is called NEST. So if you have attended the conference, I think Professor Bin Fei had attended this meeting. This at EMPA is kind of a live, I would say, demonstration for us, where all the technologies we develop at EMPA is showcased in this building. It's called NEST, and it changes. This building changes over the years. It has changed because the modules are very, very flexible. We can really change the building materials. We can change the way it looks inside. And this is a very nice place. If you come to EMPA at one point, this is the place to visit at the end to see all the nice development we are doing. So, and thank you for your attention. If you have questions, I'm very happy to answer the questions, I would say.
So before we go to the online stream questions, so we would like to ask the audience, do you have any questions?
Just feel free to ask any silly question. Anything, you know. I know it is very difficult. There's a lot of chemistry involved, but if you have something which you did not understand, I'm more than happy to answer, I would say. Maybe everything was very clear.
Yep. These thermostats are reprocessable. I mean, they can be recycled many times. But are they biodegradable also?
No, we have not checked the biodegradability because the goal is to keep everything in the loop. Yes. Eventually, if they are landfilled at one point, you see these phosphoester bonds are also labile, but it will take a long time for biodegradation to happen. So the goal of these new materials are not, they're not meant to be biodegradable. They're meant to be recyclable and inside a very close loop as much as possible, I would say. And still very functional in nature. That means they should offer fire protection, I would say. So that is the trick.
Yeah, so thank you very much for the nice presentation. In some instances, I noticed there's some kind of color change, color. Yes, and so for certain applications, will the color change kind of affect it? And just in case, maybe we need to add color, you know, to make it more, will it have any effect on the reprocessability?
So, yes, you're right. You see, in some of these development, there is a change in color. And one has to understand why this change in color happens. So a lot of this chemistry contains amine as a cross-linking agent. And amines do not like to be processed again and again, I would say. So in order to avoid that, I would say we have different chemistries we have developed. Like, for example, we have the amine-free chemistry or carboxyester chemistry. It's very easy to, I would say, well, they do not discolor with time, I would say, and they retain the shape. However, saying that the amino ester chemistry, which is kind of a different chemistry, we also retain the similar color as the starting material. They are not always completely, I would say, color free. So some of them are slightly yellow in nature because the raw materials are colored. But if you start with very high purity materials, you would have a color-free material, but also it will stay colorless as many times as you process. But yes, in some cases, you cannot avoid it. It is an inherent, I would say, problem of this material. Saying that, it's just cosmetics. The bulk properties more or less remains the same. So any small ppm level byproduct which is formed, and these are oxidized form of this material, you have color, I would say. So you're right. If you need good aesthetics for 10 times recycling, you would probably choose the right kind of chemistry. And we do have different chemistries which we can use.
So any further questions? Yep. Great.
Hello, I'm Yuxin. I'm also from the Polytechnic University, and I'm a student of Xinyan Huang, and also a group member of our SFPE. Yes, and I really appreciate your excellent presentation. And I also did some simple work about flame retardant epsilon resin. I always confused about how to evaluate the flame retardant materials from a standard rule. Maybe I know maybe we did some tests like FTIR, the cone calorimeter, the TG, and so on. But I don't know how to weight the test and give a scholar of the flame retardant materials. Yes.
So you have to understand, when you evaluate a fire performance of a material, you evaluate it for a specific application. So imagine there is a polymer material which is being a socket here, that one there, that has a different requirement than something which is a part of this door, I would say. Okay, so every material is then evaluated for its application, and one has to keep that in mind. Okay, but then saying that, there are some basic, so each application has its specified fire test, which is based on the scenario in which it may get ignited. Okay, for example, if this socket would not burn by itself, but they may have electrical, I would say, short circuit, and there is a really specific test for electrical short circuit, and that's called glow wire test. But then you can also have a flame from the floor which can ignite this socket here, and that is simulated with the UL94 test. Okay, but then obviously not all tests. If you have a flame retardant material which passes one test, doesn't mean that it will pass another test, because the fire scenario is different and the requirement is different. Okay, so an easy way to correlate fire performance of a material is run a TGA and see how much char is being formed. The less polymer which goes in the gas phase, the more, I would say, fire-proof the material would be, or flame retardant the material will be. That is one case, I would say. Okay, so that's a very simple tool you can use, but doesn't mean that it will pass all the tests, but it will burn slower. Okay, and then heat release rate of material is also very important, I would say. Heat capacity of a material is quite important. So these are small tests you can do to see how flammable a material is, okay? So, but I would say you should not really look into grading them without arbitrarily. I would grade them based on an application of fire scenario which this material may be exposed to in its use. So that's something you should keep in mind. But simple test, as I said, by just running a thermal gravimetric analysis where you see how less is a volatile produced at different temperature, is a good indication of how flammable the material is. But that doesn't mean anything. You also need to look into how much heat these volatiles are producing by measuring the heat release rate, by doing some calorimetric test. Okay, very simple test which I used to do a long time back was bomb calorimeter test, where you look at the heat of combustion of the material. That's also very good. It gives you an idea about how much heat would be produced if the whole building is burning down, I would say. You'd want to have a less heat, I would say, producing material, I would say. So yeah, you need to be aware of it.
And adding on the bomb calorimeter, it creates all the values we've been using in the FDS and all the gems that we're using in the current fire models as well. So like Dr. Gaan said, like we have a lot of range of testing based on different application of the material, the scale of the material we're going to use, and so forth. And any further question from the audience? Is there any from online stream? Okay. Well, maybe I have some follow-up question for my own curiosity. I know you very well, so I know your work to a lot of degree. But I do have a question with regards to today. So you've mentioned there's transparent coating on the material. We have a project previously working on that as well. And I was wondering, is that recyclable, or that coating itself?
Well, obviously this, if you use the covalent adaptable network as a transparent coating, we should be able to recycle it. The question is, how would you recycle a thin coating, I would say? You may have to delaminate it, so by applying heat, okay, that could be a trigger, or possibly having, I would say, light trigger could be a possibility as well. So yeah, there are different ways you can adapt the chemistry to delaminate the thin coating from the wood. Saying that, you may think of different scenario. You may actually crush the whole panel and then bind them together into a fiber board. That could be another possibility. But it doesn't make sense to just recycle the thin film, I would say. Possibly you could strip it off to recover the polymer, but it's very thin, I would say. I would rather just crush it so that the polymer is a part of the fiber board then, later on, I would say.
So just a quick follow-up question. So when it comes to recycling, you mentioned the further we go, the more energy it takes to go back. So I was just wondering, like, how do we consider a good balance between a good recycling process?
Actually, it's an excellent question. What we haven't considered in our work is life cycle assessment. So that's something we want to do in our project. Going forward, I would like to look into the life cycle assessment with environmental, I would say, chemist, and see the real assessment is then done, and we will have the numbers, and we can say for what scenario the material is it's quite suitable for. For example, we have to also assess the fact that these raw materials have to be acquired, how much energy is needed, how much energy is needed to produce this material, how much energy is needed to recover this material. So all these have to be considered at one point, I would say. Okay. Obviously, I see a bright future for these materials because at this moment, the current state of art thermostats would not be able to are not recyclable. So at least we offer hope. Obviously, the whole manufacturing of these materials have to be done by somebody, I would say, with less energy input as possible. So there is a lot of work to be done, I would say, and the industry has to adapt itself to new materials, new technology, and we need to do assessment of how big should be the loop to really be sustainable, I would say.
Well, thank you for the answers, Dr. Gan. And obviously, your research work is very meaningful and contributory to the not only the PHI community, the material and the polymer chemistry community, but to the society in general. So with that, first of all, we want to give you a big clap. Sorry. Sorry. Last but not the least, the most important question for you today.
Every time you give some new findings, very surprising to me, and you have developed some new systems for recycling, recyclable V-trimmers, and maybe turn to the page 25, slide 25. And there is the data about the phosphorus percentage, phosphorus content. And wood material with 2.5% phosphorus. So this percentage, what it is based on the pure coating or based on the whole wood? In the coating, yeah. And what's the thickness of your coating on wood? Oh, 500 micron. Yeah, 0.5 mm. Yeah. Okay, quite thin. Yeah. So the result is quite good. Yeah. Does it give intermittent, not obvious?
Yes. Yeah. Well, you can see the intermittent here. What they did was they took it off. We forgot to take picture of the of the
horizontal
cross section, I would say. But you can see this one here, giving an idea of the mushroom on.
Before, when we work on the cotton finishing, to make a cotton stable enough, flame retardant enough, the phosphorus need to be over 3.0%, 3%. So that's for cellulose. But here for wood or for the coating, really don't need that much phosphorus, and it can resist to the continuous burning. Then for the testing, how long it can be stable? If we continuous apply the flame on the surface, 10 minutes, 20 minutes, then finally it may consumed or not consumed.
I think it's a good question, but the fact that these 5 minutes of flame exposure already is quite long for us. We did not continue this test, but once you form this barrier, it more or less can shield the inner layer very good. So I would assume just from the flame itself, this test, it would be able to easily withstand for a long time, hours. But yeah, I mean, at one point, we did not do this test, and this is not a standard test. This is just a you know, this what do you call it, advertisement test, there is no standards associated. If we have to look into real applications, we need to look into the standard test methods. So
Actually, before we end, we have a small gift as a token of appreciation. So it is a small coffee cup here, and this is our recycle.
recycled bag.
Yeah, no, it's not. It's just good for environmental friendly bag.
Thank you.
Yeah. So yeah, maybe we can.
So I'm really collecting a lot of mugs these days, coffee
Yeah.
mugs. Huh?
Yeah. Thank you. Yeah, we will take a photo together, but I want to suit up myself.